Hi everyone, I'm Romain Cosson, and this is joint work with my PhD advisor, Laurent Massoulié at INRIA in Paris. This talk will be about the role of randomness and collectiveness in decision making. Let's start with a quick warm-up on zero-sum games. Classically, a two-player zero-sum game can be represented by a cost matrix, M. So for instance, rock, paper, scissors can be represented by a 3x3 matrix like this one. Now, there are two kinds of strategies that are usually studied: pure strategies and mixed strategies. A pure strategy uses only one line, for example, the first line, rock. In this case, the cost is going to be equal to 1, because the adversary picks paper. A mixed strategy uses multiple lines, for example, picking at random. In this case, the best mixed strategy picks lines with probability 1/3, and this guarantees a cost of 0. But maybe you have just one coin flip, so you cannot take decision with probability 1/3. This is what we call a barely random strategy. For example, this is a barely random strategy, and it has a cost of 1/2. Let's give a definition for any integer k. We say that a strategy is k barely fractional if it takes values that are only multiples of 1/k. Equivalently, we say that it is k barely random if it can be sampled with one uniform random seed between 1 and k. And also equivalently, if you are a group of k friends playing collectively, then each of you picks a pure strategy and the team shares the cost. This is what we call the collective interpretation. All of these notions are equivalent, and the question we ask is, how does the cost scales with k? And we ask the question in the context of real-time decision making. Let me present a simple decision-making game. Suppose you are this person who lives in New York in the 1950s. You don't like to travel, but you also don't like to pay rent, so you decide to move to Nevada. But it turned out that Nevada becomes quite expensive, and 30 years later, you sail back to Georgia. But then the 2000s, price change again, and finally you decide to move to Tennessee. So clearly you took decisions using past data, and you could not know that you should have moved straight away in Tennessee in the 1950s. The quantity we are interested in this problem is the competitive ratio. It is equal to the cost that you paid during the game divided by the best cost you could have paid with hindsight if you had known the future. This problem is known in online algorithms as metrical task systems. There's a metric space, like the US for instance, and at all times you receive the list of the costs of rent in each state. And you have to decide on a position to live. And if you can use collective nets, you can decide the position of k of your friends. The cost that you pay is the cost of rents plus the cost of moving between places. And you compare this to the best cost with hindsight that we did not opt. So the question becomes, how does randomness or collectiveness affect the competitive ratio? For k is equal to 1, the deterministic competitive ratio is equal to 2n minus 1. When k is equal to infinity, Bebeck et al. Showed that the competitive ratio could be pushed down to log squared n. In this work, what we show is that even when k is finite, you can still have a competitive ratio in log squared n, and this is as soon as k is greater than n squared. So this means that a pretty small teams of people can be competitive for this problem. Or equivalently that you can design randomized algorithms with just log n random bits. Let me say a few words about the techniques. Our idea is quite simple. It is to transform the fully fractional strategy of Bebeck et al., denoted y, into a barely fractional strategy, denoted x. The naive way to do this will be to take x that is the closest to y in the sense of optimal transport. But there is a simple reason why this does not work. In this example, if y is 0.76, then x is 1, and if y is 0.74, then x is 0.5. This means that x is too sensitive to variations of y. So we use a technique that is inspired from a physical phenomenon called hysteresis. Intuitively, by adding another term, a regularizer that takes into account the distance to previous positions, we're able to make sure that our barely fractional strategy only moves when it is really worth it. Thank you very much for your attention, and don't forget to think of hysteresis for your decision-making systems. Also, don't hesitate to get in touch.